Okay, so last time we talked about, towards the end, we talked about sequences. And so in particular, we talked about square root of 2. Right? So square root of 2, we could think about this, if we wanted to think about square root of 2 on the real line, then we have here 1 and we have 2. And we could define a sequence of numbers where the first one is 1, the second one is 1.4, the third is 1.4.1, and the next one is then the next digit in square root of 2, so 1.4.1.4, etc. And so, so this is like a sequence of numbers that are increasing, and it is square root of 2 where you're taking more and more digits, right? So square root of 2 is in some sense the limit of this sequence. And so precisely a sequence is, so we talked about that last time, but let me just remind you what that is. So a sequence is a function from the natural numbers. So f goes from the natural numbers into the real. And the value at some natural number n, the value of this function at a natural number n, this we denote, usually it's a standard notation that one denote it like this, where the n is a subscript. Okay. And so let's take a look at a couple of different sequences. So we talked that, so this here really is a sequence. Another example is where you have an equal to -1 to the power n. So, n again is this natural number. So this means that the sequence a1 is equal to -1. a2 is equal to -1 times -1, so that's 1. a3 is -1 times -1 times -1, so this is -1, and a4 is -1 multiplied itself 4 times, so that's 1. Right, so this sequence here is, it's alternating between the values -1 and 1. So it's starting off at -1, and then it goes to 1, then it goes to -1, 1, -1, etc. Okay? And so this sequence here, right, it doesn't really, right, it's not, you know, it doesn't really convert, it doesn't really have a limit, right? So this here, we'll make this precise in just a minute. So this sequence does not have a limit. An example of a sequence is a decaying sequence like this. So an is equal to 1 over n. Right, so a1 is equal to 1, a2 is equal to a half, a3 is equal to a third, and then a4 is equal to 1/4, right? So these numbers here are all positive, right? The values of a is all of them are all positive, and they become smaller and smaller, right? So you could write that sort of suggestively, this here is going down like that. And so, right, so it seems sort of obvious that this limit here, that this sequence has a limit, this here has a limit. and the limit is 0. Okay, so now let me make the formal definition. So what does it mean that a sequence is convergent? So a sequence AN is convergent to A. So A is another real number. A sequence AN is convergent to A if the following is the case. If the following hold. For all epsilon greater than 0, there exists an natural number such that if little n is bigger than this natural number, then the difference between AN and this supposed limit is bounded by epsilon. Okay, so if you think about it, on the, here you have on the real line, here you have A. And so if you give me an epsilon, so then I'm looking at A here, I'm looking at an interval around A. So this is an interval here from A minus epsilon to A plus epsilon. And the claim is that the sequence AN is converging to A if there exists some n, so that if little n is larger than this capital N, then all of these AN land somewhere here, right? All of them AN is in this little interval for n, little n bigger than this capital N, right? That's what it means to be convergent, right? But it's like for all epsilon. So you're allowed to, someone else is allowed to pick the epsilon, and then you have to prove that there exists a capital N, so that from there on and out, all of the AN lie in this little interval. Okay. So this is what it means for a sequence to be convergent. So we say that AN is convergent to A if this here is the case. And in that case, one also writes that the limit as n goes to infinity of AN is equal to A. A sequence, so if you have a sequence that is not convergent, is said to be divergent. Okay? And so now let me look at an example. So suppose you're looking at the number 0.99999, etc. Right? This number here, this number here, we really think about this number here as 1. This is indistinguishable from 1. Right? And in fact, what you really think about is that you think about that you have a sequence A where A1 is 0.9, A2 is 0.99, A3 is 0.999, A4 is equal to 0.9999, etc. Right? So AN is where you have 0. And then 9 n times. Right. If you're looking at that sequence here, right, then you have that this sequence AN is convergent to 1. So AN, this one also write that is convergent to 1 like this. So AN is convergent to 1, right? So there's various ways of writing that is convergent. You can write it like this. This means that it's convergent, and the limit is A. You can write it like this. This means that this sequence is convergent, and the limit is 1. Right? Or you can write it out in words. Okay. So this sequence, I claim that this sequence here, defined like this, and this is really how you think about this, right? When you think about this number, you sort of think about it that, this is, 0, 9, 9 with more and more numbers, 9s added, and the limit, which is really what this number here in itself is 1. Okay, now let me explain why the sequence defined this way, why this is convergent as a limit 1, okay? And so now, of course, now you give me an epsilon. So given epsilon greater than 0, then I need to find a capital N so that from there on and out, the AN is within epsilon. So we need to find, for this epsilon, we need to find capital N, so that if little n is bigger than this capital N, then AN minus 1 is less than epsilon. Right? That's what we need to do. Right? But for your epsilon, so to do that, we need to choose this capital N. So I'm just choosing, I just choose capital N. So to do that, choose capital N such that that 1 over n is less than epsilon, right? We can do this by the Archimedean property, right? So this is, so we can find n by the, such an n, and capital N by the Archimedean property that we discussed last time. Okay? But now you see, if you're looking at, if you now look at little n that is bigger than capital N, then you have that 1 minus AN. Well, 1 minus AN, actually for all n, this here is less than 1 over 10 to the power n, right? Because like if n is equal to 1, this is within 1/10 of 1, and likewise this here is in 100 of 1, etc. Right? So we have this inequality. It's actually equality in this case. This here is an equality. Right? Okay, but now you see that this thing here, this is obviously 1 over 10 to the power n is less or equal to, it's less than n, 1 over n, And so if little n is bigger than capital N, this is therefore less than 1 over capital N, but this here was less than epsilon. And that's what we needed to prove, right? So for your given epsilon, I specify a capital N, and then we need to prove that if little n is bigger than that capital N, then we come within epsilon of the limit, okay? Okay, now let me prove a little theorem about convergent sequences. And this is like, if you will, this little lemma is like the first test for whether a sequence is convergent. So theorem. If AN is a convergent sequence, then AN is bounded. Sorry, let me explain what I mean by that. I mean that then the set of AN, so let me just explain that. So then the set A1, A2, A3, etc., this set here is bounded. Okay. It's not enough to be bounded, that to be convergent, but it is a necessary criterion. Right? Let me just, as a side remark, say that if you're looking at the sequence AN that we looked at just a minute ago, this here that is alternating between -1 and 1, right? This is a bounded sequence because there's only 2 values, so it's obviously bounded, but it's not convergent, right? So, but it is a necessary for a sequence to be convergent. It's necessary that the sequence of numbers here is bounded. Okay, so now let's try to prove that. So since AN is convergent, then there is some A so that AN converges to this A, right? And so now I can just focus on one single epsilon. So in particular, if we choose epsilon to be equal to 1, then there exists capital N, so that if little n is bigger than this capital N, then a little n minus A is less than 1, right? This is convergence just applied to this single epsilon, right? Okay, and so this is the first observation. The second observation is that if we now look at all the AN that are not considered here, so if you're looking at the set, this is the first capital N minus 1, AN, right? Those are the ones that doesn't fall in under that this little n is bigger than the capital N. So this set here is finite. So obviously, so for any finite set, you have that, so there exists C, a real number, such that AN is less or equal to C for any of these guys, right? For any A in this, any AN in this finite set. Right. So this means, in other words, this means that AN is less or equal to C if N here is between 1 and N minus 1. Right. So now I look at, now I want to look at the numbers AN and this number here, right? And I want to look at, so I'm thinking about the set AN absolute value, and where N here is 1 up to 1, 2, etc., right? Well, I claim that this thing here, I can now prove that this set here is bounded. And this is just because that the first N minus 1, those are bounded by C. So I claim that this set here, so claim is that the sup of this set, where N from 1 right over all N's, the sup of this set is less or equal to the max of C and A plus normal absolute value of A plus 1. So I claim that. Right. Now this is clearly, if you're taking the first N minus 1, then we already know that they are bounded by C, right? So you just need to worry about the one starting at capital N, right? So we only need to worry about when, so this is obviously the case for the first capital N minus 1. So we only need to worry about, to show this for little n larger than capital N, larger or equal. Yeah?
Are you able to explain in the max over there why there's the absolute value of A plus 1, like the plus 1?
Yeah, I will explain this, and I'll get to this. And this is part of the proof. Yeah. So it hopefully will be clear in a minute. If it's not, you should complain. Okay, so I only need to prove that when I'm just looking at the set here, and I'm starting at capital N, then the sup is bounded like that. Right? And so then I'm looking at AN, but AN I can write as AN, I can write sort of in a stupid way. I can write AN as AN minus A plus A, right? So I can write it like that, right? And then I can just write, so I have the sum of two things. The absolute value is less than the absolute value, the sum of the absolute values. So I have this, right? But now you see that since little n is bigger than this capital N was chosen so that this here was bounded by 1, right? So this thing here is less than 1, and this here is less than the absolute value of A. Right? And so we have, for the whole tail, starting at capital N, we have that this thing here is bounded by 1 plus the absolute value of A. And for the remaining capital N minus 1, those are bounded by C. Right? And so together, all of this is bounded by the maximum of these two things. Okay. Now the next thing I want to talk about is that there's some sort of algebraic property of limits. That is often very useful. And I will prove there's 4 of these. And I will prove 2 of them. And the other one I will outline the proof of. Yeah.
So in that, the claim was that the soup is less than. So we don't need to find.
Yeah, no, you don't need to actually find the soup, right? Yeah. And the reason I want to write soup and not maximum is that, of course, if it's infinite numbers, it's not clear there is a maximum, right? So we need to use the terminology soup.
So that max of C and abs A plus 1 is not the soup?
No, that's right. It's a bound for the soup, but the soup presumably is less.
And 1 there really is just epsilon, right?
And the 1 really, to some extent, could be almost anything. Yeah, it came from the epsilon, right? But you see, if you made that epsilon smaller, then probably the C would jump up, right? Because that is, right? Because the C was the maximum of the first n minus 1. So if you're further out, then there are more numbers that you're taking the maximum over. So anyway, yeah. Okay, so we want to prove some algebraic properties of limits. Okay. So the idea is that we take, so we have 4 of these. And the first one is that you take a sequence, so maybe I'll just say throughout, AN and BN are sequences. And AN is convergent to A, and BN is convergent to B. Okay. The first property is that if you take a real number, C here is a real number, and you form a new sequence where Cn is just this real number times An, right? So each Cn is somehow almost like An, except that they're multiplied by this fixed constant C. So this here, so the first one is that Cn is also convergent, and the limit is just C times A. Okay. The second one is that if you take that A, if you define a sequence, so this is a different sequence than this one, but if you define a sequence Cn by its An, the nth element is An plus Bn, then this sequence is also convergent. Cn is convergent, and the limit is A plus B. So that was the second property. The third property, is right. The third property is that if you take a product. Sorry. So if you take An, if you define Cn as An times Bn, right? So this is a new sequence. Then Cn is convergent, and the limit is A times B. And the last property is that if the An are all of these are different from 0. So this here is for all n. And also you have that the limit here is not equal to 0, then if you define a sequence to be 1 over an, then cn here converge, and the limit is 1 away. Okay. And so I will prove sort of rigorously the first two, and I will basically tell you how to prove the other two. But the first two I will kind of write out formally as as we talked about last time, how you write formally a proof. Whereas what I'm going to discuss for 3 and 4 is very, very close to a formal proof, but it's more like what you would have on a piece of scrap paper. Okay, so now let's prove the first one. So proof of 1. So given epsilon greater than 0, So first of all, of course, if this capital C is 0, then everything is 0. So it's like trivially the case. So we may as well assume. that capital C